everybody. Let us try to look into Schrodinger's equation. We will start looking for Schrodinger's equation in one dimension only to start with. Then we can extend the same concept to maybe two-dimensional or three-dimensional case, because in that only the extension with other dimensions is required, but the fundamentals will remain the same. Now let us consider a particle with mass m in one-dimensional classical mechanics. That means this particle can move back and forth with x describing the position of the particle. Now in Newtonian mechanics, our goal is to know the trajectory of the particle. That is, we want to know x as a function of time. So that is the goal if we are trying to look into this one-dimensional movement using Newtonian mechanics. That means we are actually working with position as a function of time. Now given the initial conditions, we can find out the position of the particle. So if we are dealing with Newtonian mechanics and we want to find out the position of this particle using the Newton's second law of motion, which gives me F is equal to ma. So we can find out the position of the particle, where F is the force and mass into acceleration. So the important point here to mention is that the forces are important in classical mechanics, but forces are not very useful in quantum mechanics. So we have to understand this point right at the beginning when we are trying to expand our discussion on quantum mechanics. Now, in a conservative system where it is allowed to write a potential energy function, right? Therefore, force is the negative of the partial derivative of potential energy function with respect to x. So this is what we call as the force expressed in terms of the potential energy function v, and it's the derivative of v with respect to the position. Now, just to explain this point further, in quantum mechanics, what is a conservative system? A conservative system is one where the total energy remains constant over time. So that's what we define as a conservative system. Now, this happens when forces acting in the system are conservative. That means these forces can be derived from a potential energy function, right? A force Fx is conservative if it can be expressed as the negative gradient of a potential energy function Vx. So this is how the force can be expressed as a gradient of the potential energy function with respect to the position, the negative of this quantity. Alright, so that's what is a conservative system. Now in 3 dimension, this is equal to F is equal to minus, of course I have just explained, the del of V, this is the potential energy function, and this R vector is the position vector. R can be in a 3D system, it can be x, y, z, but in a 1D system we are taking only x. So that is work done by the force depends on the initial and the final positions and not on the path taken. So because the work done will depend on the initial and the final positions. Now if we start from F equal to ma, so acceleration is basically dv by dt. So if I replace this F with minus del of v by del of x and this v by dx by dt, so this is equal to m d double derivative of x with respect to time. The point here I want to mention is that in Newtonian mechanics, because I am taking the example of a 1D motion of a particle, right? So position, we want to identify x, that means the position of the particle. Using Newtonian mechanics, we can find out using this Newton's second law of motion, where force is given by this mass into acceleration. But forces are important in classical mechanics. In quantum mechanics, since it is a conservative system, that means the force is related to the negative slope of the potential energy function with respect to x. So therefore, we will express the force to be minus del v by del x, and this mass into acceleration is can be further put into double derivative terms, because acceleration is the double derivative of the position with respect to time. So this is basically a differential equation that we get. Now we need to solve this differential equation with initial condition. With what are the initial conditions? X 0 and v 0. That means at t equal to 0 we should know what is x and we should know what is v. Now, how difficult it will be to solve the this partial differential equation will depend on this function v. That how difficult potential energy function you have chosen, that will add to the difficulty level in overall solution. Now, in quantum mechanics, we have to forget about the intuitive ideas like force, velocity, or x. Rather, we have to rethink. Now, this is another important concept that we have to understand once we are dealing with quantum mechanics. In classical mechanics, we are dealing with forces, the velocity vector, the position, the displacements, right? But x I am mentioning here because we ultimately want to know the position of the electron. Now we want to find out the position of the electron using Newtonian mechanics. We can find out the position by using the Newton's relations that we already know that we can do it using the classical mechanics. But in quantum mechanics, we have to rethink of this approach actually. Now we need to look for a concept called wave function, and is denoted by psi and will depend on x and t. So this is wave function. Wave function is dependent on x, which is the position of the electron, and time. So we have to look for the position of the particle at a particular time also, right? So this wave function will tell us the information about the particle. Now psi will also allow to measure, because in quantum mechanics we will not be able to exactly know where the particle is. We will only be able to affix a probability to the position at a particular time. So that means at this time the particle will be at a certain point with this much probability. So we cannot say say the position of the electron or the particle is this uh, with certain terms, but we can express. So therefore the quantum mechanics will be a kind of probabilistic concept to find out the position of the particles. Therefore quantum mechanics is the probabilistic description of the universe. How do we find psi of xt? That means how do we find the wave function of the particle? That means how we will find out the properties of the, how we will find out the information about the system in terms of the wave function. That means the probability in terms of probabilities. So we need to actually solve Schrodinger's equation. So Schrodinger gave an equation. This is the Schrodinger's equation. In order to understand the quantum system in a better way, or in order to understand, in order to find out the wave function, we have to solve this Schrodinger equation, right? Whereas in classical mechanics the laws were well established. We could have used the Newton's laws to find out the position of the particle, but in quantum mechanics the case is not so simple. So therefore Schrodinger gave an equation in terms of wave function, which is psi, and this is the equation we will have to solve in order to find information about the system. This equation is the time dependent Schrodinger equation, and this is actually, this equation is we can prove it also. I will not prove it here right now, but we can prove that this equation is actually F equal to ma of the Newton's world, this Schrodinger's equation. where psi is the wave function and psi is analogous to xt, that we were trying to find out the position in the classical world. So psi is, we are trying to find out the wave function or the information about the system, but we will find out psi by solving this Schrodinger's equation only in terms of probabilities, but not with certain terms. So this is just the introduction of the Schrodinger's equation. Now this Schrodinger's equation actually will have three terms to look, if we look closely. Now the first, the left hand side term is the time derivative of the, with respect to time, the derivative of wave function with respect to time. We can say that this is the overall energy of the system, right? Now this term in which the double derivative is there for psi with respect to x, now this we can say that this is the kinetic energy term. Of course, in actual terms we can prove this, but I am just trying to explain in this video that this is the total energy, this is the kinetic energy, and this is the potential energy. So this is the energy equation basically represented in terms of the quantum mechanics world, in quantum mechanics world. And psi is analogous to x, which we want to find, x we want to find in classical world. In quantum world we want to find psi. So we will obtain psi by solving this Schrodinger's equation, which is basically iota h cross del psi by del t, that's the time derivative of the wave function, minus h cross square by 2m double derivative of psi with respect to x square plus v. V is the potential energy function and psi is of course the wave function. So this is overall Schrodinger time dependent Schrodinger's equation. Time dependent, why? Because we have one term in which the wave function is dependent on time. This is a one-dimensional version of the Schrodinger's equation, but if we use the other coordinates also, like x, y, z, all three, then with the little modification we can express the same equation in terms of Schrodinger's equation for 3 dimensions. But this is Schrodinger's equation in time dependent Schrodinger's equation for 1 dimension. The ultimate job is to find psi, which is the wave function, because wave function will give us the actual information about the system. We will look further into the Schrodinger's equation and we will try to solve the Schrodinger's equation for certain cases in the coming lectures. Thank you.